5.1, rates of change and the number e. So a couple of notes just on exponential functions. We're in Unit 5, which is the derivatives, rate of change of exponential functions. So just to get ourselves back into the swing of things and understanding that, exponential function is any function that involves exponential growth. So growth where each term is multiplied by a repeated factor, or exponential decay, in which each subsequent term is repeated by a multiple, by a factor of between 0 and 1. Anyways, some of those look like population. So you could do like a population situation where you might have p with respect to t. Population over time is your initial population. Maybe you're talking in terms of a doubling time, and then you have the number of doubling periods with respect to days. Another example would be radioactive decay. Radioactive decay. You might be looking for a certain amount or wondering how much of an amount of a radioactive material will be left after a certain amount of time. So you start with the initial amount. In this case, you have exponential decay. So the factor is a decay factor. It's between 0 and 1. And then you have the number of decay periods, and that will give you the amount remaining. Another example would be investments. In investments, they can typically be modeled using an exponential function. So let's say you invested $500 and you're earning 8% on that $500 year over year. Then after 1 year, you'll have 500 times 1.08. After 2 years, you'll have 2 factors of 1.08. And so this is exponential. And the amount that you have after a certain number of years will fill in the blank here. Again, these look like this or this. Growth, decay. And what we want to start doing is talking about the derivative of exponential functions. So we're talking about the rate of change. So if we just take a look at this exponential growth function here, we can see, if we're talking about the slope, we can see the slope is also always positive, and the slope is always increasing. So it turns out that the derivative function of an exponential function ends up being another exponential function. And generally, which we'll discover, is the new function, the derivative function, will be lower than the original function. The derivative function, the rate of change of the original function will create a new function that is an exponential function that is a vertical stretch or compression of the original function. Okay, we'll learn more about that later. It turns out that there is a special exponential function, y, and we don't have to write this quite yet, but the function is going to be y equals e to the power of x, where the derivative function of y equals e to the power of x is actually the same function as y equals e to the x. So the derivative function lands right on top of the original function. So e is a special number when it's in an exponential function. Its derivative will land right on top of it. So we're going to talk about what e is. The symbol e is an irrational number whose value is defined by the symbol e is an irrational number whose value is defined as the limit as n approaches infinity of 1 plus 1 over n to the power of n. So as we're taking the limit as n approaches infinity, you can see this fraction is getting closer and closer and closer to 0. So the value within the brackets is getting closer and closer and closer to 1 from above. And then we're multiplying it by itself an infinite number of times. It turns out that this value is between 2.71 and 2.72. So E is approximately 2.71 or 2.72. It's somewhere in between there. Now we do get more decimal places in the next. It's actually 2.718. So it's a lot closer. If we were going to use 2 decimal places to estimate it, we'd use 2.72. But virtually always we'll just use the symbol E because it has an exact value and our calculator knows the exact value. Okay, what else did we talk about here? Another note, the derivative of an exponential function is a function that is a vertical stretch or compression of the original function. So far we don't know what that stretch or compression is for a particular exponential function. We'll learn that in 5.3. But for now we know that the derivative of an exponential function is another exponential function, and it's simply a vertical stretch or compression of the original function. So the only thing that's happening there is that you're getting a multiplier out in front. That's either a fraction between 0 and 1 or a number greater than 1 to cause a stretch. And the last thing that we have here is another note on what E does, which we've already talked about. The derivative of y equals e to the power of x is y prime equals e to the power of x. It is the same function. Okay, that is 5.1. Essentially, the practice problems just have you sketching exponential graphs, and the graph of f of x equals e to the power of x, where e is approximately 2.72, and that'll give you a better understanding and get us back into the world of exponential functions.